Right now, as you're watching this, our entire planet is slowly wobbling through space like a cosmic spinning top. And that wobble, it's literally controlling whether we're heading into an ice age or a tropical paradise. I'm talking about something called Milankovitch cycles. And before you click away thinking this is some boring geology lecture, stick with me. Because what we're about to explore connects the movement of planets millions of miles away to volcanic eruptions here on Earth, and ultimately to whether your distant descendants will be ice skating in Florida or growing palm trees in Alaska. Let's start with the simple truth. Earth's climate has always changed. Long before humans showed up with our cars and factories, this planet was cycling between ice ages and warm periods like clockwork. And for the longest time, we had no idea why. Enter Milankovitch, a Serbian mathematician who, about a century ago, figured out something incredible. He realized that Earth doesn't just orbit the Sun in some perfect, unchanging path. Our planet actually does 3 different dances through space, and each one affects how much sunlight hits different parts of Earth at different times. Think of it like this. Earth is constantly changing its relationship to the Sun in 3 ways. First, there's eccentricity. That's just a fancy word for how oval-shaped our orbit is. Right now, Earth's orbit is pretty circular, about as round as you can get. But over roughly 100,000 years, it stretches into more of an oval and then back to circular again. When we're at our most elliptical, there's a roughly 20% to 30% difference in solar radiation between when we're closest to the Sun versus farthest away. That's huge. Second, obliquity, which is the tilt of Earth's axis. You know how Earth is tilted at 23.4 degrees? That's not constant. Over 41,000 years, that tilt wobbles between 22.1 and 24.5 degrees. More tilt means more extreme seasons, hotter summers and colder winters. Less tilt means milder seasons overall. And third, precession. Imagine Earth as that spinning top I mentioned earlier. Not only is it spinning, but the direction it's pointing changes over time, completing a full wobble every 26,000 years or so. This is why 13,000 years from now, summer in the Northern Hemisphere will happen when Earth is closest to the Sun instead of farthest away like it is now. Here's the kicker. These 3 cycles don't happen in isolation. They interact with each other, creating this incredibly complex pattern of climate forcing that has paced Earth's ice ages for millions of years. When these cycles align in certain ways, massive ice sheets grow across the continents. When they align differently, those ice sheets melt and sea levels rise by hundreds of feet. Now here's where things get really interesting. Scientists recently discovered that volcanoes are apparently paying attention to these orbital cycles too. I know what you're thinking. How can a volcano, miles deep in the Earth's crust, possibly care about how Earth orbits the Sun? Great question, and the answer is both simple and mind-blowing. It comes down to weight. Massive, incomprehensible weight. During ice ages, ice sheets can be 2 miles thick. Imagine the weight of ice covering entire continents. We're talking trillions upon trillions of tons pressing down on Earth's crust. Then, when Milankovitch cycles shift and the ice melts, all that weight vanishes relatively quickly. This process is called glacial unloading, and it has dramatic effects. When you remove that much weight from the crust, the pressure on the mantle below drops significantly. And when pressure drops on hot rock that's almost ready to melt, it melts. It's like opening a bottle of soda. The pressure release allows gases to escape and things get active. But it's not just ice. Sea levels also play a role. When ice ages end and sea levels rise by 400 feet, that adds weight to the ocean floor. When sea levels drop during ice ages, it removes weight. These pressure changes, even though they seem small compared to the mass of the planet, are enough to influence when and where magma wants to erupt. Scientists analyzing volcanic ash layers in deep-sea sediments found something remarkable. Volcanic activity shows clear peaks at 26,000, 41,000, and 100,000 year intervals. Those are exactly the Milankovitch periods. Volcanic eruptions in the Mediterranean and around the Pacific Ring of Fire tend to cluster about 4,000 years after the fastest sea level rises following Ice Age maximums. When volcanic activity increases during deglaciation, it releases massive amounts of CO2 into the atmosphere. That CO2 contributes to warming, which accelerates the melting of ice, which causes more volcanic activity, which releases more CO2. It's a self-reinforcing cycle that may help explain why Earth transitions from ice ages to warm periods relatively quickly. But, and this is crucial, we're talking about processes that unfold over tens of thousands of years. The climate change we're seeing today happens over decades. Completely different ballgame. All right, now we're going to zoom out, way out, all the way to Mars. A brand new study just revealed something that sounds like science fiction, but is absolutely real. The mass of Mars, a planet 140 million miles away, directly controls the timing of Earth's ice ages. Here's how they figured this out. Scientists ran computer simulations where they varied Mars's mass from 0, like no Mars at all, to 10 times heavier than its actual mass. Then they watched what happened to Earth's Milankovitch cycles. The results were stunning. That 100,000-year Ice Age cycle I mentioned earlier, it's driven by Mars. When they removed Mars from the simulation, that cycle largely disappeared. When they doubled Mars's mass, the cycle got stronger and slightly shorter. Mars is literally tugging on Earth's orbit through gravity, changing how elliptical our path around the Sun becomes. Then there's the grand cycle, a 2.4 million-year pattern that modulates all the shortest cycles. This one is entirely created by the gravitational interaction between Earth and Mars. No Mars, no grand cycle. Double Mars's mass, the cycle shrinks to 1.4 million years. Even Earth's 41,000-year tilt cycle, which is primarily stabilized by our moon, gets affected by Mars. Make Mars heavier, and Earth's tilt cycle lengthens to 45,000 to 55,000 years. Make Mars 10 times heavier, and it stretches to about 50,000 years. Now, there is one cycle that doesn't care about Mars at all, the 405,000-year rhythm. This one's driven by Venus and Jupiter, and it's so stable that geologists have found it in rock layers spanning hundreds of millions of years. It's like the universe's metronome, ticking away regardless of what Mars is doing. But here's what really gets me. Mars is tiny. It has only about 11% of Earth's mass. It's this little rust-colored pebble in space, and yet it exerts critical control over our planet's long-term climate patterns. Why? Because in orbital mechanics, it's not just about mass, it's about position and timing. Mars orbits relatively close to Earth on cosmic scales, and its orbital period creates these resonances with Earth's orbit. It's like two pendulums hanging next to each other. Even if one is much smaller, they can influence each other's swing. So what does all this mean? Why should you care that Mars controls our ice ages or that volcanoes record orbital cycles? First, it completely changes how we think about habitability in the universe. We've discovered thousands of planets around other stars, and for years, the focus has been on finding planets in the Goldilocks zone. Not too hot, not too cold, just right for liquid water. But this research shows that's not enough. You can't just look at a planet in isolation. Imagine we find an Earth-like planet at the perfect distance from its star. Great. But if it has a supermassive Mars equivalent nearby, its climate cycles could be radically different from ours, maybe so extreme that complex life never gets a foothold. Or maybe it doesn't have a big moon like ours to stabilize its tilt, and its axis wobbles chaotically, creating climate chaos. Habitability isn't just about being at the right distance from your star. It's about the right neighbors in the right places. It's about the entire architecture of your planetary system. Second, this research reveals that Earth's habitability, our habitability, is the result of a cosmic accident. Mars formed with exactly the mass it has. If it had been twice as heavy, Earth would have experienced ice ages on a completely different schedule. The entire history of life on Earth, the evolution of complex organisms, the rise and fall of the dinosaurs, the eventual emergence of humans, all of it unfolded against the backdrop of climate cycles determined by planetary positions that were set 4.5 billion years ago. We are, in a very real sense, the children of a specific planetary arrangement. There's something deeply humbling about all this. We like to think of ourselves as separate from the cosmos, like we're down here on Earth doing our thing, while the universe does its thing way out there. But that's not how it works. The wobble of Earth's axis, determined by the Moon's gravity, the shape of our orbit, tuned by Mars and Jupiter and Venus, the pattern of volcanic eruptions responding to ice sheets that grow and shrink based on those orbital changes, the climate that allowed our species to evolve, paced by cycles set in motion by planetary migrations billions of years ago. We're not separate from any of this. We're woven into it. Every glacier, every volcano, every ice age, every warm period, they're all connected to this vast cosmic dance of gravity and motion. And now, for the first time in Earth's 4.5 billion year history, one species, us, is conscious enough to figure all this out. So the next time you see Mars in the night sky, that little red dot, remember, you're looking at one of the primary architects of Earth's climate. That distant world is tugging on us, shaping the ice ages our ancestors survived, influencing the volcanic activity that helped build our continents. We live in a cosmic neighborhood where even the smallest neighbors play surprisingly important roles. And understanding that neighborhood, that's how we learn to understand ourselves. The universe is vast and strange and more interconnected than we ever imagined, and we're just beginning to read its story.